pre-calculus students, welcome to section 11.3, the cross product of two 3D vectors. We will be doing examples 34 and 38. And what a cross product is the cross product of two vectors in space is a vector. It's not like the dot product where it produces a value. The cross product of two vectors in space produces a vector that is orthogonal. Remember, that means perpendicular to the two other vectors and the plane that they lie on. The cross product is said, when you say it, it's U cross V, is used in physics, especially with magnetism in some different formulas and also with forces. So, because when you find the vector, if we called it W, that is the cross product of U and V, then that means that if W is equal to U cross V, then W dot U and W dot V would both be 0. The dot product would both be 0 because you made a vector that is orthogonal or perpendicular to U and V. Okay, now the formula for the cross product looks complicated, but it actually kind of is easy to follow. If you have vector U, which you know is U1, U2, U3, and vector V, which you know is V1, V2, V3, then U cross V is equal to a vector. So notice there's 3 parts to it. One part, right, the first component, comma, second component, comma, and third component. Now the first component would be U2 times V3 minus U3 times V2. Okay, so easy to follow. If you just have to be super careful, right? You know where your U1, U2, U3s are, V1, V2, V3s, right? The second component is the opposite. The negative of U1 times V3 minus U3 times V1. And the third component is U1 times V2 minus U2, V1. Again, I know this seems complicated, but take a look. Notice that the U and the V's are always in order. Notice for component 1 that you're using 2 and 3 and 3 and 2. Notice for component 2, you're using 1 and 3 and 3 and 1. And for component 3, you're using 1 and 2 and 2 and 1. So whatever component you are working on to write the cross product, you are using the other 2 components. Now, an interesting application, if you have a parallelogram and you write 2 adjacent sides of that parallelogram as the vectors U and V, then if you do U cross V and take the magnitude of that, you do get the area of that parallelogram. Just something different, right? So problem number 34, find a unit vector perpendicular or orthogonal to this vector U and this vector V. Okay, so the first thing we're going to do is do U cross V and get that or that vector that is orthogonal to these 2, right? So we are going to do U cross V. I'll probably use my calculator with the numbers on number 34, and that will give us a vector perpendicular to those 2, and then we'll write it as a unit vector by finding its magnitude and dividing each component by that. So I'm going to try to be super careful here too. So here we go. The first component would be U2 times V3, right? So U2 times V3, right? That is a negative 14 times a negative 15. Better pull out the calculator, right? That is 210. Minus, I am right here now, U3 times V2. I literally point at it to help myself. U3 times V2 would be 5 times 28. 140. Go. The second component will be the negative. Do not lose that negative. And it will be U1 times V3. U1 times V3. Right? 7 times the negative 15. Which I should be able to do, but just trying to be consistent. A negative 105 minus, now I am at U3 times V1. U3 times V1. 5 times 14, 70. For the last component, it is U1 times V2. U1 times V2. That's 7 times 28, 196 minus U2 times V1. U2 times V1, negative 14 times 14 is minus 196. Okay, let's do a little bit more work here then. 210 minus 140, 70. Negative 105 minus 70 is a negative 175, and now it's positive. And 190, this would be 196 times 2 is 392. Wow, those are big numbers. Okay, now let's find the magnitude of this vector so that we can write it as a unit vector. Wow, that's big. Okay, let's go ahead and do that. Let's call this vector W, and let's find the magnitude. That would be this 70 squared plus 175 squared plus 392 squared. Add them up and take the square root. 70 squared plus 175 squared plus 392 squared. Add them up and take the square root. And that gives us the square root. You know what? It gives us a decimal. You know what? Let's make it a decimal. 434.959. Here we go. So to make it a unit vector, because that would be a really big square root, I will divide each of these by the magnitude. And frankly, I think it's okay to leave it like this. We could turn each of these into decimals, actually do this math here, here, in here, and have a final decimal answer. I think that's okay. I think it would have also been okay. This would have been a very large number to leave it. The magnitude is the square root of 70 squared plus 175 squared plus 392 squared. Have that answer, that radicand, underneath the square root, but that would have been really big also. Now, one thing I do want to show, though it's not necessary, here's our final answer right here, is I do want to take the vector, just going to make a box right here. The vector W that we found is 70, 175, and 392. I just want to do the dot product W dot U and show that it is 0. So I'm going to do that on my calculator. So that's 7 times 70. Again, this part isn't really necessary. I just want to show that we did make a vector that is orthogonal to U, plus, and then I'll have a negative 14 times 175 plus, and 5 times 392. And we do get a 0. I also want to show, not that it's necessary, though I think they ask it sometimes in the book, that W is orthogonal to V by doing the dot product. So I'm going to do 14 times 70 plus 28 times 175 plus negative 15 times 392. And we do get a 0. All right. Sorry for the huge numbers. Okay, we're going to look at problem number 38 now. Hi, we're back for number 38. We are going to find the area of a parallelogram with these vectors as the adjacent sides of the parallelogram. So if you drew these two vectors and made two more parallel side to u and to v, you would have a parallelogram. And we are going to use these two adjacent sides of a parallelogram written as vectors to find the area of that parallelogram. And that formula is right here. We're going to do u cross v and find the magnitude of that vector. Now, what I'm going to do this time, we have our vectors written as the sum of unit vectors. Let's write them in component form and use that. So we have 1, 2, and 2. Much nicer numbers than our last problem. Notice that here we do not have a j in this vector, so it is 0, j. So we have 1, 0, and 1. Here we go. Okay, let's carefully do the cross product of, and we'll write it as vector w when we do u cross v. So let's take a look. Here we go. This would be u2 times v3. u2 and v3, 2 times 1 is 2, minus u3 v2. u3 v2 would be 0. Second component, minus u1 times v3. u1 v3 is 1 minus u3 v1. u3 v1. Last component, u1 times v2. u1 times v2 is 0 minus u2 times v1. u2 times v1. Well, these are much nicer numbers, aren't they? So that vector then would be the vector 2. Here we have 1 minus 2, so a negative 1, and now it's a positive 1 and negative 2. And the magnitude of that vector would be the square root 2 squared plus 1 squared plus negative 2 squared. Right, so we have 4 plus 4 is 8, plus 1 is 9, and the square root of 9 equals 3. So the area of that parallelogram is 3. Came out very nice. Go. Have a great day. Enjoy section 11.3.